I think we are live. So, hello everybody. Welcome to the Latin American webinar on physics. Today we have a very nice webinar. It's going to be your host, our guest, Carlos Alvarado, the speaker of this webinar. For all the people that is following the transmission, you can ask questions using the chat in the YouTube. So, any question you can write it there. We are gonna read it at the end of the talk of Carlos. And of course, don't forget to follow us in Facebook and in Twitter to be updated with the latest news about the webinar that we are doing here. So, Carlos Alvarado, he got the PhD in the University in Notre Dame in US, and now he's postdoc at the Tsinghua University in China, in Beijing. So Carlos, that is here present, he's going to talk about the from particle physics model to gravity wave spectrum, a recipe. And welcome, Carlos. And you can start your talk whenever you want.
Okay, thank you very much, Roberto and Alejandro. Thanks for the invitation. I have known the webinar since long ago. I have many friends that have participated, and this is my first time, so I hope you enjoy it. So let's start sharing. What about now? Okay. Yeah, as Roberto said, this is going to be about gravity waves, at least a partial portion of it that is related to more closely to particle physics as opposed to the general relativity and black hole physics side. Okay. And I will try to connect these two things in a very specific way. It's more of a review, and I think you're welcome to ask questions if they are very quick, but I think they are encouraged to be pushed until the end due to the format of the seminar. Okay. So gravity waves, probably you have heard about them, because in 2016 there were a couple of discoveries regarding black hole mergers and the gravitational waves that they produce, and that were detected by this interferometer LIGO. Okay, that time it was about two astrophysical objects interacting and doing something. In this case, I'm going to talk about a slightly different phenomenon that is still able to be a source of gravity waves, which is due to phase transitions. Phases of matter can be characterized by microscopic systems that have well-defined thermodynamical properties. And one example that we know since very early age is, the three states of matter: solid, liquid, and gas, and the fact that they change abruptly into one another depending on the value of temperature, but also depending on the pressure. Okay, so you have well-defined states of your system, and here is going to be similar. The roadmap to the talk is going to be, let me talk about effective potential, the scalar effective potential, and let me talk about bubbles, which are the objects that produce these phase transitions and how they nucleate in time. Also, the velocity with which these bubbles grow in time. And let me arrive then at the gravitational wave spectrum that connects quantities that appear in these previous quantities. And let me finish with some software tools and examples of phase transitions that we can calculate and get a spectrum from. So the effective potential, when you have a theory with a scalar, you can have something called the effective potential. It encodes the interactions and also the terms of the free theory all together. And I'm going to consider the finite temperature extension of this quantity. And I'm going to talk about, I'm going to consider also one loop extension of both in t equals 0 and t non-zero regime. So the three-level potential is the object that you are probably most familiarized with. Sometimes it sets the leading properties of the phase transition. For example, if you have terms like cubics or other even powers, but you also have one loop corrections given by the Coleman-Weiber potential, which is basically draw the diagrams with one loop and the interactions of your theory. Uh, just remember to renormalize it correctly and keep a good track of the degrees of freedom, because you have fermions which contribute with a sign that is not the same as for integer spin particles. Okay. And a crucial object of this effective potential is the field-dependent masses, which depend on a constant background that can give you the value of the mass at the different phases of your system. Uh, you can look at a review of thermal QFT techniques to find out how to correct by thermal effects your Coleman-Weiber potential. Uh, and you have these kind of functions that depend on the field-dependent masses and the temperature. You can expand them. Sometimes if you keep some terms in the height expansion, you might notice that uh, the leading order term goes like t squared times the mass of the field, which again is going to be different depending on whether the field has taken its vacuum expectation value or not. But more importantly, that means that you are extending your scalar potential by a term that is quadratic. Okay, sometimes quadratics are certainly not the leading term, but because they are multiplied by the temperature, they are gonna overcome all others and will dominate the how do you say, the boundness of the potential. For example, if you have a negative quadratic, this term is gonna make it overall positive at high energy. Okay, so you're gonna be considering the B masses, which are these thermal corrections to the T equals 0 masses. And you need to do this carefully because gauge bosons, only the longitudinal ones acquire a correction. And this has an important effect in the character of phase transition. Okay, so imagine that your trivial potential did not have a cubic, okay? But there is still one generated when the temperature turns on, okay? So here you can distinguish two configurations, one in which you can have a second order phase transition. And by that, I mean that if you look at the minimum of the potential at very high energy, it is placed on the origin. But as the temperature drops, it moves to a finite value of the field, but it doesn't in a continuous way, okay? So this is a continuous curve. So that's the way it changes the vacuum expectation value. This is the background field that gives masses to particles, for example, in the electroweak mechanism of symmetry breaking. But it could be also that if your cubic is strictly non-zero, a thermal one, for example, you're gonna end with this feature, which is a barrier that makes the minimum be at the origin at high temperature, at least at a temperature higher than a specific value called the critical temperature. But as you lower the temperature, it channels via quantum or thermal effects into this new minimum, which is actually the global minimum after you lower the temperature low enough. Okay, so I'm in a position here to talk about the first ingredient for gravitational wave spectrum. What you need is to know the energy density released by the phase transition. So what is the energy that you have in total? You have radiation, but you also have the energy contribution from the scalar potential. But when you take the difference, you're gonna have the piece that that depends on the difference between the minima, okay, at a specific temperature, with I'm gonna call Tnuc. It means nucleation. I'm gonna describe nucleation more carefully in a few slides. So this is gonna be the energy you have to convert into gravitational waves, at least partially. So you can use thermodynamics to write this difference in terms of effective potential, okay? Because effective potential can be understood as a pressure in the thermodynamical sense. So this is how it goes, okay? And let's normalize by the total radiation of the universe to make a parameter called alpha, okay? that we are gonna use in the gravitational wave spectrum. Um, I'm assuming that your universe is radiation dominated. Otherwise, you need to put the total energy in the denominator. That's fine. The problem is that we still do know the nucleation temperature, okay? Or the temperature at which you have your system starts changing from uh, the unbroken to the broken phase. And that's what we do now. So the bubble nucleation rate. The bubbles of the space-time that contain a non-zero web um, have a nucleation rate per volume such that there is just the false vacuum when the temperature is high enough, but eventually, again, by the fluctuation, these new minima became favorable energetically, and they start popping. Okay, so when you reach a certain specific temperature, they start popping. Okay, and when it lowers enough, then you might end up with a lot of bubbles that eventually overcome and take the whole universe. Okay, uh, but it's not enough that they appear. They also need to be uh, to maintain their growth. Okay, so that's what I'm gonna discuss next. So they grow if the volumetric change in energy overcomes the surface uh, negative contribution. Basically, you have volume, because you are changing the VEV, you are changing the favor minima, but you also have tension because there is an interface around your bubble, a certain radius. So there is a radius such that after you have a gain, uh, a net gain that is positive, the bubbles not that just popped out from the vacuum, they start growing at a specific velocity. Uh, it's not necessarily the speed of light. It depends. I'm going to talk about this in a few minutes. It could be a constant velocity. Okay. Okay. But what else? What is a specific form of the nucleation rate? It depends on the action between the minima, the object that you know as the integral of the Lagrangian. Okay, which in Euclidean time, in the Euclidean action, which uses imaginary time so that you end up with an Euclidean measure, just because in thermal QFT, that's the way you can work. The action reduces at a high temperature to this object, S3 over T, okay, which depends again on the effective potential and the kinetic term. And you would like to minimize this object such that your nucleation rate has the largest possible value. Now, if you plot this object in temperature, it looks like this, okay? Here I can distinguish between a purely quantum tunneling, for example, when the temperature is very low and is described by this magenta curve, or it can be strictly thermal and be described by these orange curves, okay? So depending on the configuration you have, it can just take a minimum, or it can just reach the zero value. All of this depending on whether your barrier disappear at some point in your potential function. Okay. Uh, Now the actual value of this function that minimizes this action is going to be called the bounds for historical reasons. Okay. So this your field is going to satisfy, when you minimize the action, an equation which is called the bounds equation, and it looks like this with these boundary conditions. Very basically, what you have, okay, I want the vacuum expectation value uh, within some radius to be the new one, the one which is non-zero, but I want to have outside my bubble the value zero, and to be that way until infinity. That's why you have this kind of profile. Okay. And the way to solve this is not very difficult, because there's an equivalent system, which is a particle rolling in a negative potential, okay, with some friction that depends on this 1 over r term. And you consider r to be a time in this new way of looking at the problem. But you want to find a very specific solution that minimizes the action. So what you can do, for example, if you have a computer, is to release your initial state from, say, this position and let it roll. The goal is to have the black ball reach the origin so that it connects the minima that you're interested in. If it is too low, uh, it won't reach the zero and it will just oscillate, okay? If it is too high, it will reach there, but it won't stay there. It's gonna oscillate again. This is called the undershoot, overshoot algorithm. It's trial and error until you have a very specific position such that at the end, the particle doesn't move from the origin, okay? Uh, so you get these solutions that oscillate, just as I said. But the true one is when you find the nicest solution in this algorithm, the one that gives you the actual curve. Uh, you may end up with a very thin profiles or thick, depending on your model parameters. Some people avoid solving this equation by postulating an ansatz for this function, which is like a tangent hyperbolic, something like that. But you can always automatize this, sorry, with some software, which I'm gonna describe near the end of the talk, such as bubble profiler, Cosmos transitions, or any bubble, okay? In particular, I'm gonna talk about Cosmos transitions. Very well. Um, okay, let's continue with the nucleation rate still. We know how to calculate the nucleation rate once we have an idea of what we want, which is we want at least one bubble in a volume of space that has Hubble size. Well, not one, it might be just order one, okay? But you want at least some uh, number that is at least small to start your filling your universe with the new bubbles of the new vacuum. So you set up this equation. You want at least one bubble per volume, okay, which you can see here. This gives you an equation for the nucleation temperature so that it must satisfy this equality. And you know, when you do this for an electroweak scale effective potential, you find that, okay, this takes a value about 100 GeV, which is kind of expected because at the end of the day is the scale of the electroweak phase transition, okay? Uh, uh, and the action over the temperature takes mostly values around this number. Since you have logs, even if you have Planck scale here, the sensitivity is low due to the logarithm. So yeah, we have the second ingredient for gravitational wave spectrum, which is the nucleation temperature. Uh, Almost immediately, we can get another ingredient. We would like to know, to have an estimate of how long the phase transition takes uh, to happen or to fill most of the universe, okay? So we can parameterize that duration by a parameter beta, okay, defined as the time derivative of the thermal action, okay. It can also be seen as the first uh, coefficient, the first coefficient of the Taylor expansion beyond the nucleation temperature. Here I'm using interchangeably nucleation time and temperature time because I'm assuming radiation domination. So you know how to go from time to temperature. It's basically T goes as inverse of temperature squared, okay? And the important thing is that this parameter is gonna give us at the end an estimate for the frequency of the gravity wave, okay? So far we have three parameters. Something that tells you the release energy, when it happens, and for how long it stays happening. Okay. The less trivial ingredient is gonna be the velocity of the bubble, the velocity at which it expands, the wall velocity. Uh, you know, if the balls were just in a universe that is vacuum, this will simply expand forever. And with an increasing velocity, it can become ultra relativistic at some point. And the force driving the expansion is going to be the difference in effective potential at zero temperature. Okay. But in the physical world, that is not true. You have a universe that is filled with a relativistic fluid, which is the standard model plasma. So you need to take into account the interaction between the bubble wall and the particles of the standard model, especially those that get masses, such as the fermions, the quarks, and the electroweak gauge bosons, and even the Higgs itself. Okay. In this case, there is the driving force due to your difference in height of the phase transition, but there is also friction. Okay. And there are several ways to model the friction, and it's actually non-trivial. One approach is to, set up your equation of motion for the Higgs plasma and postulate this term, where you have for velocity dotted with a derivative of the Higgs. Okay, so you can say that as a friction, you expect that it depends on the velocity of the fluid. Okay, the actual way is to do a numerical calculation that involves Boltzmann equations that are very complicated because you need to take all of the possible processes between the wild and the standard model. But anyway, the way the bubbles can grow when there is a friction is they can either be a detonation or some other solution that I will describe shortly. And how you find this is that basically you can go to, for example, Landau thermodynamics and set up a discontinuity and two fluids at every side, each of which has its own thermodynamical quantities different from the other side of the wall. When you have the outer velocity being larger, you have a detonation. So practically the fluid is at rest in front of the wall, but that causes the high velocity just inside the wall, okay? And this is the profile it takes if you compute it numerically or analytically, only in the case where your system is very simple. The other case is when the inner velocity is larger, or in other words, when the growth is not so fast. Basically, what you have is the bubble is hitting the standard model fluid, and outside you have a shock front. It accumulates there with high velocity, and you have this kind of profile, okay? Um, okay, this is done numerically, but it's its own topic. So let me just say that this is a fourth ingredient, the wall velocity, that in the most optimistic case, you would like to be large, such that you can have a significant gravitational wave signal. Okay, so let me just recap very quickly what happened. We have a parameter that measures the energy release by the transition in your scalar potential. So parameter that measures the duration of it, the time or equivalently temperature at which it happens, and how fast the bubble expands. Beta and the velocity of the wall are not necessarily similar in size. Okay, it depends on which kind of bubble you have. So we can now proceed to the gravity wave spectrum. But before that, let me say that gravitational waves are disturbances in the space-time metric, such that in a wave-like solution, they satisfy the linearized equations of motion. The spectrum of gravitational waves at the end of the day depends on, at least from phase transition, can be parameterized in terms of these quantities. There are other kinds of gravity waves, such as those by inflation or those by black hole mergers, which are the most famous ones. But these ones, the ones that are sourced by phase transition, have a specific shape and behavior under these parameters. Okay, so this was analyzed some time ago in the 90s by Kaminkowski and collaborators. They basically found that the spectrum as a function of frequency takes a form that goes like this, where you have a function of all of these phase transition parameters, some efficiency parameter, because not all of the release energy goes into gravity waves. Since there is standard model fluid, some energy goes into heating the standard model, some other piece goes into disturbing it, making motion for it. And the remaining part is the one that goes to gravity waves. Okay, S of F is what gives you the shape of the frequency spectrum. Okay, so the very first thing they did is analyze. Okay, I need at least more than one bubble to source a gravity wave. One single bubble cannot do anything because you need to predict the uh, spherical symmetry, because gravity wave is sourced by tensor perturbations. Okay, so you need collisions of bubbles to do something. This is a non-trivial problem, so the first approach was to consider the energy that is imprinted on the wall by just looking at the uncollided part. Okay, and they found that the results can be fitted by some function G and S. But shortly afterwards, well, sorry, not so shortly, 10 years almost later, uh, this is the kind of shape it has. Okay. You can see that there is not just these four quantities and the frequency, there are also the degrees of freedom of the standard model, which I'm gonna take as just all of them around 100. There is not much difference if I take another values. And there is a lot of frequencies in a gravity wave, but the peak one is gonna take, the size of the peaked one, it's gonna be something like this. And I am taking the redshift into account, because one thing is to produce some frequency, and another thing is when you want to detect that frequency, because it must travel. Uh, you need to wait long enough until you receive the signal, so you need to do the redshift also. So this is one way of generating gravity waves by colliding bubbles. You can also try to look at the fluid outside the bubbles and see what happens after you produce some collisions. You are also perturbing the fluid. Uh, your collision can be so energetic that you ionize standard model fluid. This it's topic. It's a topic on its own. But what they found is that you can also parameterize with a similar function. However, you have different powers of the quantities. The efficiency goes to a different power, and more importantly, remember that I said beta gives you the duration of the phase transition. The power is not the same as with the previous one. Sorry. Uh, Before we had -2. Sorry. Now we have -1. So you have an extra factor of beta over Hubble time nucleation. And this just reflects that, even after the collisions have mostly gone, you still end up with a perturbed fluid that is ionized and turbulent. So they last longer. But the even more importantly, that the turbulence is the gravity waves that you generate by sound waves. When you perturb the fluid outside the bubble with coherent motion, which goes beyond the envelope approximation that I mentioned before. This is the shape of the spectrum found by numerical simulations. Basically, you take a box, you make a fine grid, and you model the interaction between the Higgs and the standard model plasma in a discretized way, and you take time steps and you let the system evolve. Uh, these are simulations that are very detailed and actually very nice, because just look at the figures. Basically, at high temperature, you have uh, something like one image that I showed some slides ago. But after some time, you get a very violent environment, okay, in which there are many bubbles colliding. And actually, you can look at movies of how these bubbles start growing in this link. Okay. So, okay, how do these three spectra look when I plot them together? Just for the sake of seeing how they compare to each other, let's take all of them at the same parameters, you know, these three set of this. And let's be very uh, ingeniously optimistic and say that the bubbles are completely relativistic and that the efficiency to which they transmit gravity wave energy is total. So just let's send both at one. So the scalings in frequency go like this, okay? Uh, you can see that sound is prominent. Uh, However, you might have all of three happening at the same time. So basically the spectrum you generate, the one that is measured by detectors at the Earth or in space, is the black curve, okay? So somehow you make the sun be even more dominant, you know, you will have a different decay at the end. It depends on which one is dominant. Um, but it's important because the scaling is important because, you know, detectors go like this. They have certain sensitivity to some value of the amplitude of the spectra, which is the vertical axis. Uh, but you know, if they were larger, sorry, if they reach deeper in this plot, uh, it's gonna make a difference whether or not you have a tail or not. So you need to pay attention to the tail when your detector is not let's say, the best that you have, okay? Or in other words, suppose that my curves were lower and you have a detector that just barely curves in this region. Certainly you would like to have very good control over whether or not it can detect gravity wave spectrum in this region, okay? Now, how do these curves change when you modify the, the ingredients of the gravity wave spectrum? Again, alpha gives you the release energy of the scalar potential. So in very naive terms, when you increase that energy release, basically you increase the height of your curve. That means that you increase the amplitude of the gravity wave. Now, if you increase the temperature at which your transition happens while keeping the velocity of the process constant, or the other way around, you find that this displaces into higher frequencies, okay? I'm gonna show in a few slides the spectrum overimposed with the detectors. But now I just want to clarify how this is modified with your parameters. Uh, there is a lot of software that can help you with this. I'm not an expert, but at least I'm familiar with Cosmo transitions. Just very briefly, let me say there's some free publicity for the program. But anyway, uh, suppose that you want to uh, code these two potentials. Notice that one of them has a tiny barrier, the other one has a very large barrier between two minima. You put them there and you can just immediately calculate the bubble profile, which is how it changes from the inner side to the outer side. And also what is the action that, of your system when going from one minimum to another. You get for these two curves something like this. Notice that the action can be very tiny or very, very, very large, depending on the barrier, okay? Um, okay, so I mentioned an algorithm to do this in one dimension. Unfortunately, when you go to two dimensions, that means when you have more than one field that is transitioning, the system gets, the calculation gets complicated, and you need algorithms that actually compute minima in two dimensions. Not just minima, something that gives you the minimal path of this calculus of variation. At the end is calculus of variation. Again, this is one example in Cosmo transitions. Another cute feature that you get in this program is that you can get the how the minimum changes in temperature. And all of these curves are three phases of the system. Zero, starts growing, and then jumps discontinuously to another value. uh, One example of all of this implementation, uh, actual implementation of all of this is the dimension six Higgs extension. Suppose that you increase your Higgs potential by a term like this. Um, you will have depending on the choices of your quadratic and the lambda here, you may end up with something like this: a minimum at the origin and a minimum that is different outside the origin. But this is just at t equals 0. Again, if you include thermal effects, such as the ones I described near the beginning of the talk, you are lifting this minima, right? Or in other words, as time progresses, you are lowering it again. So let's put Cosmos transitions to work for this model. Basically, the only parameter that is free in this implementation is the cutoff of the dimension 6 term. Basically because the quadratic and the quartic are fits, because you still want to get the mass of the Higgs and the BEP to their values that we know and have measured. So the action, for example, divided by the temperature looks like this. And the nucleation temperature looks like this. And this reproduces some results of the literature. How the alpha parameter that controls the energy release evolves with the cutoff looks like this. What I did is basically make a grid in this space and let Cosmos transition find the action in minimal action at every point, okay? So since I have the action, I can get beta. Here is alpha because I know my scalar potential. And just assuming perfect spectrum in which you have ultra relativistic velocity, this is how it looks, okay? Compare against several reaches for different detectors, such as a LIGO, LISA, this Chinese detector Taiji, and some other feature detector called BBO or Einstein telescope. But this can be done more in general. You can translate many models. What you need is these 4 quantities, okay? So there are some online tools as well, and even repository of different models. You can also be a good contributor and upload your own model. Or you can just test which kind of curves you get when you choose some points. For example, for a singlet scalar without C2 symmetry, you get this kind of contours of alpha and beta. That's useful because you can see if your model that does many other things may also give you a detectable gravitational signal. So I am finishing here with some final comments. One is that, okay, we review in a very raw and quick way the parameters that control the gravity wave spectrum when you analyze phase transitions that are of the first order, which means they have a barrier, so there is a discontinuity. Um, Now, if you detect if you have an observation that might point out to a specific model, but it's not that simple. You need also to discern between different models, okay? But that's up to you to work out. But basically, the amplitude depends on the strength of the phase transition, and the frequency, as I said, depends on the relevant energy scale. For example, electroweak phase transition is going to give you frequencies 10 to the minus 2 hertz up to probably 1 hertz. But if you want 10 to the 5, 10 to the 4 hertz, which is an A LIGO reach, you need to consider definitely not an electroweak phase transition, but probably something in the hidden sector in which you have multi-TeV vacuum expectation values of, for example, a singlet or a dark Higgs, and so on. Okay, so you can map a gravity wave spectrum once you know the effective potential, but assuming that you have control over the wall velocity. Again, for electroweak case, this has been done extensively, but it's a very non-trivial problem, especially if you have hidden sectors that have non-trivial interactions with the standard model. Or moreover, for example, through all of the talk, I have assumed that you have radiation domination. maybe you have a period of matter domination. So you need to take into account that to get the correct wall velocity. So here is where I expect some of your questions, and many thanks for your time.
Thank you very much, Carlos. So it was a very interesting talk. So for the moment, people that is interested to ask question to Carlos, you can write it in our YouTube channel. You can follow the chat that is in the live transmission. For the rest of you that is here in the Zoom session, we can start to ask to Carlos any question. You can unmute yourself and make questions to Carlos. And don't forget for the people in the audience to either to subscribe to the YouTube channel, but also to follow us in Facebook and Twitter to be updated with the latest news about the webinar. Since this is the webinar number 98, we are very close to arrive to the 100 webinars. So it's a very, very nice milestone for us. So, okay, you can start with questions. It seems that Alejandro want to ask.
Yeah, thank you, Robert. Thank you, Carlos, for the nice talk and for being awake at that time in China. I have two very naive questions. So the first one is, could you please again remind me, how can we get a reliable estimate of the bubble wall velocity and those frictional effects in your model? Because it seems you need to, yeah.
Okay.
Could you please comment that again?
Nice, yeah. So I show that you can get, depending on the velocities of the wall at each side, you can get either one propagation way, which is called detonation, or another one, which is called deflagration. Let me go back a few slides. Yeah. That has to do with an equation that you set for the velocities at each side of the wall. However, there is not enough, that is not enough to determine the thermodynamical system, because you have four unknowns. You have four variables, which are the two velocities and, for example, the two temperatures, T inside and T outside. Forget about the pressure and density, because these are function of the temperature, because you know that this is a fluid, okay? So you have four variables here. By the continuity equations, there are two of them. And actually, you know T plus, the temperature outside the wall, because that is the nucleation temperature. So, okay, now you have three variables. However, for example, for detonation, the velocity outside is the wall velocity, because basically the fluid is unperturbed outside. So you have two equations in the velocities, and two variables, which are the two themselves. You need one more equation to determine the temperature inside the wall, okay? So that's where you need to, to consider one more equation that models the friction. This equation is nothing else than the equation of motion of the composite equation of motion of the Higgs and the plasma. Basically, you take the Lagrangian of both and you find the equation of motion, as you know. And you need to solve for T minus. However, depending on how you model this friction term, you may need to, that can make the calculation non-trivial. I mean, it won't be analytical. You need to do things numerically. Let me see.
I see. So yeah, so that was my question. Under we have that under control, we might get a.
Yeah, you need to properly model Higgs and plasma interaction. Actually,
but that's a model. That's just one model, right? Like, I might get that T minus from another model or something, right? Like,
no, T minus is gonna be determined by your system.
Okay.
It's because it needs to satisfy the fluid equations across the wall.
At the boundary, yeah.
Yeah. So, for example, here is how you actually get the wall velocity. For focus on this one, detonation. You know alpha. I just say that the velocity outside is the wall velocity. So the only unknown is T minus and B minus. Okay. So when you solve all of the system of equations together, you get, okay, inside the velocity is this, and a consistent wall velocity that you get from the equations is this one, which are very close and also very close to one. And there is also a similar story for the other propagation. But yeah, you solve a system of equations in the velocities and temperatures.
Thank you. And then my last question was, could you please go to your, I think was one of the last slides about the detectability, like when you show Lisa. So yeah, no, yeah, that's right. So this one seems that that is very hard to detect at the moment, in the sense that, in particular for the tails, right? Like I don't know if the BBO will be part of that, and yeah, for like future instruments like Lisa, it's out of its sensitivity. Even for like future ground experiments like Einstein, is also out of the scope, right? Like, and that was our only hope to observe this. Is that
right? This is a particular model which I call the dimension 6 Higgs. Okay. And for this spectrum, I chose it's not here, but I chose alpha of size 0.1, just like here. Okay. And I also say that when you increase alpha, the release energy, the amplitude of the curve grows. So, okay, so if you want this to touch, for example, Lisa, which is at least more close to us in time than BBO,
yeah,
I would just pick alpha larger, okay, at least 5 times larger. And I do that by lowering the scale of the scale lambda of the dimension 6 Higgs. So I didn't do the curve, but I think it just barely touches Lisa.
I see. But yeah, so but in any case, it's very hard to detect, right? Like, because for Lisa, we will have this, I don't know, background noise of white dwarfs, like even in the bucket here, like at 10 to the minus 2 point something here in your scale, then this will be really buried in the noise, right? Like it will be hard to model and detect.
Right. Well, I don't remember how the noise goes, but I think it's kind of flat, at least in this region. So yeah, that's a good point. You need a model that produces a strong peak.
See, okay. So yeah, so it's okay. Thank you, Carlos.
Thanks.
So do we have more questions? We have one question from the YouTube channel. He's asking Felipe Ferreiras de Freitas. He's asking, for the nucleation temperature, it's always true the ratio to calculate the temperature. You can also write that. You can read it also, the question in the chat of Zoom, in case.
Sorry, let me.
I mean, yeah, in the case of you want to see the detail of the question.
Okay, chat. For the nucleation temperature, it's always true the ratio to calculate the temperature. Sorry, I think I don't think I understood well this. Let me go back to the slide when I show.
And yeah, and maybe Felipe can make a follow-up question, and it takes like a couple of seconds since we see it.
Probably, maybe you refer to this one. Let me know, Felipe.
Okay, for the moment that Felipe can write like a follow-up question, or to explain a little bit more his question. I have a question about the. Okay, Felipe is gonna write. He wrote in the chat in YouTube. So, yeah, he's asking about the S3 divided by 140.
Okay.
It is always through this kind of ratio.
For electroweak phase transition, whether it is 2 Higgs doublet model, dimension 6 Higgs, or other construction, I think it stays between 130 and 150. So it's a kind of a fits, not fits, but it barely moves, again, due to the logarithm here.
Okay, so it's a kind of stable point for some say.
Yeah, people like to use this 140 to just quickly do estimations, no matter their model. Again, as long as it is electroweak.
Yes. So, Carlos, I have a question about the, I mean, well, people, if they want, they can write more questions for you, also here in the people of in the Zoom session. So, okay, Felipe is making a follow-up question, is asking
Sure.
if it is model dependent, this number.
Yes, because if by model dependent you mean that this is not necessarily an electroweak transition, that means that the VEPs and the temperature, the critical temperature involved, do not have to be electroweak scale at all, do not have to be 100 GeV. So it is model dependent. Multi-TeV phase transition will give you, in a dark sector, for example, will give you very large numbers here.
Okay, so I'm gonna do my question now.
Sure.
So, Carlos, I was wondering if there is any relation, for instance, with the meta stability in the standard model. I mean, this effect can affect the stability of the Higgs potential, the back expectation value of the Higgs due to temperature correction, or kind of a feedback between the two sectors.
I expect that if you extend your standard model Higgs potential with new terms, both the new ones that you are putting there and the thermal corrections that come with them, plus the thermal corrections of the already fixed terms that you have in the standard model, I expect all of them to move your perturbativity criterion. But well, I'm not entirely sure. Sorry, because let's see. For example, for the dimension 6 Higgs potential, I mentioned that you are actually just introducing a new parameter, the cutoff, okay? The mass and the quartic are fixed by the Higgs mass and Webb. And as perturbativity, the metastability, as you mentioned, it has to do with the value of lambda, right? And in this case, lambda, I want it to be 0.13, no matter, regardless of this new term, right? So yeah, I'm not sure now that you say it. What I can say is that the running will also change due to the new physics. Yeah. So I think that if the running changes, because the metastability is done taking into account running, right? So yeah. I would bet that it changes.
Yeah. No,
I just don't remember to which order in the thermal corrections the metastability study is done.
For the Higgs, yeah. I know that for the standard model alone without temperature, I guess the latest calculation was done to next to linear orders, or two loops. And in that sense, and that level you found that the standard model is metastable. I mean, we are just between
right. Yeah, I remember the plot with the 3 regions.
So I know that in the standard model, any extension of the standard model, you can move this stuff to either to the metastability or to the stability of the sector. But now, since there is this effect of bubbles and other phenomena that maybe can impact the Higgs sector, also can.
I think that you are changing it simply by adding new physics and the thermal effects that come from them. Yeah, I'm positive that that's the case. But on the other hand, when people do models that predict a gravity wave spectrum, I think they want to have viable baryogenesis by electroweak phase transition. I mean, electroweak baryogenesis. And they want a detectable spectrum. So probably the honest thing to do is to redo your perturbativity. If it is that it changed to the unstable region. Yeah.
Okay, thanks. So, is any other question from either the audience and the people here in the Zoom? If you can, if you want to ask
Let
question to
me
Carlos, you can
see
unmute
the
yourself
chat.
to feel free to do that.
I don't see any new questions in the chat, but of course we have more minutes.
Yeah, we
Let's
have
see.
a small delay between YouTube and what is happening now. We have a boost between the two frames.
Yeah, let me know if I went very fast. I think I went very fast through a few slides, but yeah, I can talk about these quantities. The thing is, there's a lot to say because this is hydrodynamics plus thermal field theory plus all of the gravity wave uh, uh, spectrum. There's a lot to say of all of this, but the message I wanted to convey is that you can just take your models, and as long as you calculate these four quantities, you can start getting predictions for a gravity wave spectrum. And it's not difficult to plot the spectrum. You can use these tools, or you can do parts of this analytically and some others numerically. It's up to you.
Yeah. So one question now that you just passed the slides, when you were saying when you go to 2 dimensions, you have to deal with a very hard calculation, no? I mean numerical calculation to
Uh,
find the path between the two minimum.
Let me, yeah.
But is this? I mean, this is the
Begin.
method that you're using now. But is there other trends to try to make this kind of calculation?
I have seen about two methods. One of them, well, first of all, you cannot do the undershoot algorithm because you are in 2 dimensions. You cannot just push the wall and try to get it to rest at the end because it can go sideways. Okay. So one method is that they use the undershoot algorithm for the tangential component and make the program correct the trajectory in the perpendicular direction of the path so as to minimize the action. I forget the name of the method, but it's just geometrical algorithms that are not unrelated to the particle physics model building. But
So
yeah, there are many papers on Higgs and singlet in 2 dimensions, and but they don't spend too much time on the algorithm. They just run it through these programs.
yeah. So one further question in the sense that the same that you were talking now, in the sense that when you were assuming the formation of a bubble, a nucleation and so on, do you expect that the bubble, if there is only one bubble in your volume, do you expect that it's spherically symmetrical, or this is just an approximation? Because then
Uh,
for the gravitational wave, you need that to have the asymmetry because you want the perturbation in the tensor.
right.
Or
I
it's
think
just
one expects the solution that minimizes the action to be spherically symmetric, either in 4 or 3 dimensions. I'm mentioning the 4 because it can be purely quantum or just thermal, which goes to 3 dimensions because you break the time symmetry by the temperature. I think since you expect them to minimize something, which is the action, they are modeled as symmetric to start with. But I'm not completely sure if to which degree that assumption is mandatory.
no, yeah, because if it is not symmetrical, you would start with gravitational wave from the
Exactly. Yeah, there should be an easy um, argument to this, right? Because you will have just by a single bubble
yeah. I don't
some
know if it's a
signal.
kind of cosmological principle to have isotropic and
Uh,
kind of you must start with
well, if
about
you go back to the action, I mean, to the question for the, where is it? Yeah, to the question for the field, for the Higgs. Its action is symmetrical in spherically symmetric in 3 dimensions. Right. I don't know. Probably if you do this in non-trivial Corf spaces, you might get an asymmetry from the beginning. Yeah, I'm not sure. That's my guess.
Carlos, we got two more questions in the YouTube chat. So the first one is from Felipe Villazon. He's
Yes.
asking, what application could this model have beyond the study of gravitational waves? Very broad question.
Let's see. Okay, one that I skipped over because it was not the focus of the talk is that all of these quantities, the energy release, the rapidity to which it happens, and the wall velocity, even if you don't care about gravity waves, they are completely required to determine, to see, for example, if you can produce electroweak baryogenesis. Why? Because for electroweak baryogenesis, you would like to have an asymmetry that is transmitted just outside of your bubble wall, okay? And depending on the value of the wall velocity, you can tell if that Sphaleron processes that gives you the baryon asymmetry happens or not. Actually, one problem with all of this picture is that if you want to do that baryogenesis, you would like the wall to expand kind of slow so that the asymmetry builds up outside. But for gravity wave to have a detectable signal, you want the velocity to be large. So there is a competition of effects there to get both a gravity wave spectrum that is detectable and baryogenesis. So yeah, long story short, to answer your question, yes, for electrowave baryogenesis, this is very, very important. You know, if you generate the baryon asymmetry, not in the electroweak way, but due to a phase transition in other sector, it's the same story. It's simply not an electroweak, but I don't know if you can do that. But anyway, yes, completely useful.
So the second question that we have from the YouTube chat, thank you, Felipe, for the question. It's the
Thanks.
question now is from Felipe Orjuela, and he's asking, would like to ask if, I mean, if QCD phase transitions can also produce gravitational wave signal, and what is the difference with respect to the electroweak?
A good question, right? Okay, about QCD, what I can say is the following. You have a nucleation temperature that is around 100 MeV. So I would like to get the energy release by the transition. Okay, the answer is I don't know. You can try to obtain the 4 ingredients for the QCD phase transition. At least we are all familiar with nucleation temperature or critical temperature in this case of order 100 MeV. But I would like you to give me the energy release alpha and how long it takes, the size of beta. I think there is a paper by Line that talk about this, but I don't remember if this gives you a signal because I need to know alpha, the energy release. It's probably also at the scale of 100, maybe at the QCD scale. So in any case, it's just about plugging in the relevant scale in the spectra. But since it's QCD, it's not just one single field that interacts with the standard model plasma. It's now you have the analog of the field is a quark condensate, right? So I'm not familiar with how this happens.
So, well, okay, I guess Javier can answer. I mean, can write in the chat if he need the further explanation, so on. But now, because we are running out of time, just to now that you were mentioning this, I got a question. In the sense
Sure.
of, I mean, usually for the case of gravitational wave from black hole merger or so on and so forth, the source of your gravitational wave are very strong intensity gravitational fields. I mean, objects
Right.
that generate with very strong gravitational field. In the case of these gravitational waves, the source of the gravitational waves are not so strong fields, or I mean, fields of gravitation that are producing, or in the sense of what happened in the case of I don't know, modified theories of gravity, which you have an extra contribution due to, and then okay, if it is very weak fields that are producing gravitational wave, but you have so many in the universe that you have a sizable signature,
Right.
would and maybe it's completely pointless to see the
So
modification of
you
gravity.
like to compare the relative sizes of these different sources of gravity waves?
Yes, I mean, I know that the stuff that LIGO measured is very strong signature because you started with very massive objects. But in this case, since they are distributed in the whole universe, but they are building up, building up, building up the final
Right.
signature.
Okay. Since this detection by LIGO, you can tell that. Well, let's for a LIGO. So it's actually a projection a few years from now, about 3 years or five, of the current LIGO setup. That is already 10 to the minus 10. Okay. I just show an electroweak example that can be improved, but not beyond the tip of the LISA reach. So LIGO is probably around here. I don't remember. Or probably something like here. But that tells you that it's gonna be 10 to the minus 9 or 8, which seems to be, I mean, it's clearly stronger than something that you can get with this kind of electroweak phase transition source of gravity waves. So um, I would say these are subdominant to the black hole ones, just by looking at the relative frequency and amplitude. Um, but you need to know overall how possibly large can you make phase transition, not just electroweak. How much can you raise this amplitude to compare the best phase transition curve to the typical black hole merger one?
Okay, so just there is a comment in the YouTube chat. Antonio Delgado is sending greetings to you. So
Hello, Antonio.
so anyway, so I think it's time to close this session. First of all, I want to thank Carlos for the very nice webinar and to be here in this webinar session, in the webinar cycle of the law physics. And for all of you that is following the transmission, you can also look previous webinar in our YouTube channel. And of course, you can keep in touch with us via our social media. So next week, we have a new webinar from Paola Ferrario for IFIC in Valencia. So everybody is welcome to follow up, to continue visiting, continue with this series, to watching the latest news in science research. So for all of you, thank you, Carlo, again.
Thank you, Roberto and Alejandro, and any other organizer.
That are here.
Thank you very much. And thank you to all of those who asked questions. By the way, what do I do with the follow-up questions in YouTube?
You can answer in the comments of the YouTube, or either they can contact you directly.
I cannot access YouTube right now.
Because yeah. don't worry, we're gonna make a way that you're gonna receive questions via in some.
People can find your data on our webpage, and then they can find you over email. That would be the best way.
Yeah, I did not include it in the slides, but my email is Carlos, my name, at gmail 00@gmail.com.
Okay, so for all of you, you can write it down, either also to Google his name plus the university, and for sure you're gonna get some info about that. So for all of the people following the transmission, so now we're closing the transmission. So see you next time. See you next week. Bye-bye.
Thank you very much. Bye-bye.
Ok, ahora sí, estamos fuera de,